Our final lesson here in Chapter 3 is Lesson 4, where we're going to learn about some additional topics in probability and counting. We're going to focus primarily on how do you figure out how many total outcomes there are in the sample space, depending upon whether order matters or not. So we want to be able to find the number of ways that a group of objects can be arranged in order. We want to also be able to find the number of ways to choose several objects from a group without regard to order, and then we'll use these counting principles to help us find some probabilities. So first we want to understand the difference between what we refer to as permutations and combinations. Permutations are where you have an arrangement of objects that have an order. Okay, so for instance, if I'm going to, if I have 4 runners that are going to run a relay on the track team, I know that any one runner can only run one leg of that relay. So if the runner runs leg 1, he or she may not run leg 2, 3, or 4. Then there's 3 runners remaining to choose from to run leg 2, and so on. The order in which those runners are selected matters, and therefore finding the number of arrangements of those 4 runners would be an example of a permutation. Well, permutations always use factorials. Factorials are basically just the product of all integers at or below the one given. So for instance, 6 factorial is the product of the integer 6 and all integers less than it down to 1. So 6 times 5 times 4 times 3 times 2 times 1 is the same as 6 factorial. There would be 720 arrangements possible if order mattered. With regards to my track example, there are 4 runners. I have 4 to choose from for the first leg. Then I only have 3 to choose from for the second leg, then a remaining 2, and then finally just 1 person remaining for that anchor leg. So the total number of arrangements of runners on that relay team would be 4 times 3 times 2 times 1, or 4 factorial, which is equal to 24. So let's take a look at this example from a Sudoku puzzle. The objective of a 9x9 Sudoku number puzzle is to fill the grid so that each row, each column, and each 3x3 grid contains the numbers 1 through 9. How many different ways can the first row of a 9x9 Sudoku grid be filled? So here we're talking about just this first row. Well, obviously in that row, as you saw, I've got to have the number 1, 2, 3, 4, 5, 6, 7, 8, and 9. And the order matters because that's going to change the puzzle if the order were different than the one originally selected. Therefore, this is a permutation, and since there are 9 boxes to fill with 9 different digits, there would be 9 factorial different ways to arrange those digits. And if you multiply 9 by 8 times 7 all the way down to 1, you get 362,880 different ways to arrange just the digits 1 through 9 in just row 1 of that puzzle. Now, most scientific calculators have a factorial button on them, and we can try and see if we can determine where that factorial button is on your respective calculator when we're together in class. Now sometimes we're going to be arranging objects where order matters, but we're not going to arrange them all. So for instance, I might say I've got 10 runners to choose from, only 4 of which will be selected to run this relay. Well, order matters, therefore it is a permutation. But since we're not selecting all 10 of those runners, then this is 10 permutations of size 4. We're only going to use 4 of them. So to determine all the different arrangements, we'd have to take n which is the total number we're selecting from, factorial, 10 factorial in this case, and divide by n minus r factorial, and r is the size of the group that we've selected. So in this case, that would be 10 factorial over 6 factorial. Now, that would be a lot of work unless I use this little shortcut. I can start to break down the bigger factorial into the product of the integers less than it, but stop when I get to the 6 factorial that I have on the bottom. Because what happens then is if I stop there, then these 6 factorials cancel, and my answer will be the product of 10, 9, 8, and 7. So let's say we want to find the number of ways of forming 4-digit codes in which no digit is repeated. This is very similar. The digits 0 through 9, with the digits 0 through 9, there are 10 of them. 1 through 9, there are 9 of them. Add in the 0, now you've got 10 different digits to select from. We're creating a 4-digit code, so we're selecting 4 of them. And therefore, we've got the same scenario that we had with the runners on the relay team. We've got 10 permutations of groups of size 4. That would be 10 factorial over 6 factorial, and when simplified, is equal to 5,040 ways. Now, sometimes we have things that are called distinguishable permutations. And this is where you're putting things together in an order that matters, but you have different types of objects that are being arranged, okay? When you have a situation like this, and not to worry, I'll do an example, you've got to consider first how many total objects do you have? That will be n. But then second, how many of each type are there? So maybe there's type 1, and there's type 2. And you're going to arrange some from type 1 and some from type 2 from those n objects. Then what you can do is the following. Let me demonstrate this with an example. Let's say that a building contractor is planning to develop a subdivision that consists of 6 one-story houses, 4 two-story houses, and 2 split-level houses. So we have 3 distinguishable groups. Those 3 groups altogether have a total of 12, because 6 plus 4 plus 2 is 12 houses. And we want to determine in how many distinguishable ways can the houses be arranged. Well, what you can do is you can just take, the basic rule is take n factorial and divide it by the product of n1 factorial times n2 factorial times n3 factorial. So you can see here we've got n factorial on top, and it's being divided by the product of 6 factorial, 4 factorial, and 2 factorial, because that's the number in each of those distinguishable groups. Now we can break this down in the same way I did in the last example. 12 factorial I can start to break down as 12 times 11 times 10 and so on, down to the biggest factorial on the bottom, which is 6. So I've got a 6 factorial that's going to cancel that 6 factorial. Then I can start to break down the next factorial. 4 factorial would be 4 times 3 times 2 times 1. Well, 4 times 3 is 12, and that'll cancel that 12. And then the remaining factorial in the denominator is 2 factorial, which is 2 times 1. And so let's see, this 2 can go into 8 4 times. This 2 can go into 10 5 times. And so really, a simple way to get that 13,860 distinguishable ways is just to take what remains and multiply them together. 11 times 5 times 9 times 4 times 7 is equal to 13,860.